was it?
I'm not allowed to start. We've got an official starter. So.
Oh, an introduction.
Yes. I wouldn't know what to say.
Are you ready to start, John?
Yes.
Awesome, I'll just introduce you. Thank you so much for coming today, everybody. Good afternoon and welcome to Mona Vale Library for our local author program. I just wish to acknowledge the traditional custodians of these lands on which we gather and show my respect to elders past and present and other Aboriginal people here today. Please just take a moment to switch your phone to silent. Today we welcome to our library local author John Ball as he discusses his scientific non-fiction release, How to Solve AI with Our Brain, the final frontier in science. Welcome, John.
Thank you. And so here's my sound check. One of the things that I thought I'd kick off with, so this was back in November, we did the first one of these types of events just for a general audience on AI. And over the last 5 weeks, we've been traveling through the US and Europe presenting to universities because the thing behind the technology I'm going to talk about with artificial intelligence is also brain science and cognitive science, which adds a new dimension to how AI works. And so we flew in last weekend just for this event. I'm feeling a little bit jet lagged, but I think I'll get through it okay.
Good.
But you can see that's what I look like when I'm not jet lagged. So what we call a book, which we started about July last year. Just my background is when I was 9 years old, I was working on mainframe computers. My father had a mainframe at his office, and so I got to use all of these educational tools that were available. This is 1972, so I'm pretty old. And so I was always keen to get better and better at computers, and I spent pretty much my whole life working on understanding computers and how we can get them to emulate what people do, because the Star Trek stories from the 1960s are still a little bit beyond what our technologies do today, and are probably a little bit in front of us for the short term. The reason I think you should listen to me, in case you're wondering, is that from 1983 I was at Sydney University, and I had a lecturer that said we're never going to understand the brain because it's far too hard. And so as a 21-year-old, I thought, well, I've got to prove her wrong. And so I then spent 20 years working hard to prove her wrong, and in 2000 I explained my system on ABC radio, and I thought that was pretty good because it was had lots of people giving me feedback about how it was an innovative idea, and then I sort of dropped it for a few years. And I had to recall that when Marvin Minsky was collaborating with me back in the 1980s, the MIT AI guru that was behind lots of things in the AI field, he said to me that it's not just a question of coming up with a good idea that you can write about. You actually have to prove that it works as well. And so in the early 2000s, I thought, well, okay, next thing I've got to do to convince people is write some software that does this. And so for the next roughly 20 years, that's what I've been doing. So I'll show you both of those aspects today. And the purpose of the book, How to Solve AI with Our Brain. This is the dog-eared version, but we have some others at the back. How to Solve AI with Our Brain. We thought it would be kind of amusing to have the fact that we're using our brain to solve AI, but it's also how our brain works that we use to solve AI. So, bit of ambiguity there, which was kind of fun. So, this is one of the purposes of today to sell my book. But if you go back home and you go onto Amazon, you can find it. There's also a Kindle version, and after the event, we'll have some signed versions out the back. There's probably no book collectors here, but since I've written this book, I've then done my research on people who write books, and the first editions that also get signed are actually quite valuable, apparently, assuming that the book's successful. And because this is a very important book, well, who knows? It could be a good investment. So we'll have some of those after. Okay, so what I'm going to talk about is AI, so artificial intelligence, how the brain works, and cognitive science. So what's cognitive science? It's all the sciences that ago that kind of fed into AI. It was formed at about the same time in 1956, and the idea is that if you have psychology, we can observe what people do. Psychology tells us a whole bunch of things about what people can do. So that's part of cognitive science. So is philosophy and a whole bunch. The other things like linguistics.
Okay.
And for me, linguistics is probably the key to understanding the brain, because it's a difference between humans and other animals, and it's easy to measure. So if we look at this model, it shouldn't be revolutionary, but if you look at today's tech giants that are doing large language models or generative AI, and apologies for me just throwing a whole bunch of acronyms out. I do this stuff all the time, so just pick me up if I say something that doesn't make any sense.
I would encourage that everybody feels free to say, what does that mean? What is that acronym?
Yeah, convert that into English, please. I can probably do that translation. So all languages start with some sort of representation. So words or phrases go into that. So that's the thing that you can measure. You can write that down. But what that should connect to is some sort of meaning. So if you say, give me that book, that's the English for it. But give me that book has something to do with somebody picking this thing up and handing it to me, which isn't linguistic. It's just something in the world that's being done. So that should be independent to language. So that's what this semantic representation or meaning represents. And then there's this other thing which the guy who created this theory spent like 40 years on it. And I ask him lots of questions because he works with me for the last 10 years. And he had this thing called discourse pragmatics. And I always said, well, I understand how things have to be in context. If you say something, it changes depending on what the context is. And here's his model. And finally, I found out that discourse pragmatics means context. So after only 10 years, I worked out the basic building blocks of his model. But let's have a look at what some of the variations are. So if you take this really abstractly and you just say syntax this and semantics that, it doesn't mean anything. But if you take a real example, so here's an example from one of the textbooks. The man gave the woman the book. So you've got the man, which is like a phrase, gave is the verb or and then you've got the woman the book. So the book's going to the woman and the book is the thing being passed across. So that's how we do it in English. So a couple of words, a verb, and then a couple more phrases. But in some languages, you can see here, actually I can see because I'm really close, but I don't know if you can see that.
Yeah.
It says the man, the woman, the book, it to her he gave. And that's the verb, it to her he gave. So it's like a phrase of its own, it's a sentence of its own. And then these things are applied to it, and the brains of people that speak that language, doesn't click very well, but it's like that for us in English. So it's got...
What language would put it like that? The
Oh,
man, the woman, the book.
I'd have to look it up.
Oh, sorry, I thought you might know. No, that's
No.
okay.
A lot of Aboriginal languages have it like that.
Oh, did
Okay.
Yeah, I mean, it sounds, but if you change it around, the her and him and whatever, it gives a complete different context.
Right.
And it's all sound-based, but it's basically that.
It's
Right.
very
Right.
easy to be misunderstood, I think.
You do that with software too. You define the things you're talking about and then you make them do things.
Right. Okay, so this is one language, and just there's English, and then here's the complete opposite. You've got this verb followed by the man, the woman, and in that particular language, it probably means the woman saw the man, but it could mean the man saw the woman. And so again, people need to use context to solve that.
Right.
And the history of AI has always said, no, we need to just have a grammar that works this out. And then the problem is you get this ambiguity, which is, does it mean the woman saw the man or the man saw the woman? And then it's unsolvable.
Yeah.
And then the best solution to having ambiguity is statistics. And fast forward from the 1950s to now, people have done just amazingly expensive computations to try and work out all that ambiguity in real time. And that's what's led to the pinnacle of all of that, which would be the large language models we see today. So anyway, I'm never going to finish if I keep digressing. Sorry,
I was just interested, so linguists are quite involved in this.
Right, yes.
Are they?
Yeah, so if we take, I brought a couple of books. So when we were travelling, I had to travel really light, but I really like being able to hold up a book just to give people a feel for what the science is. So this is 1,000 pages, which is the most recent Roll and Reference Grammar book, and it just describes the starting point, and then there's like 20 scholars that write chapters in it that explain parts that apply to a bunch of languages.
So the answer is yes, very linguistics based.
Yes.
Yeah.
So, and so all of this comes just straight out of linguistics textbooks. And the interesting thing is, if you're a linguist, people say, well, how many languages do you speak? You know, I'm not really a linguist, but...
You understand the structure of the language.
Right, yeah, how the language works. So this is the language-dependent part, how the words go together. This is the language-independent part, which is the meaning. So you've got here, the man does some activity, which causes the dealer to have the car, who doesn't have the car before, and the man to not have the car. So that's if you give the dealer the car. And there's a lot of variations of that, but this is language independent, so that's like the book part. And then over here, the hard bit about context. If somebody says Taylor married Ridge, you could be like a computer scientist today at, say, Google, who'd say, well, that's a fact. I'm going to store that in my database as a fact. Now, if anybody disagrees, I can say, no, that's my fact. But that's not how language works. If you say Taylor married Ridge and it's false, the person listening goes, is this true? And they go, no, it was Brooke who married Ridge. So you would correct the person on the spot, and then you could argue about it. But it's possible to have, so facts relate to context. Facts aren't just something independent to everything. We see it in newspapers all the time. They have one newspaper that says this politician's evil, another one will say this politician's a god. Somehow they can't both be true, but they're both facts in context.
None of them are.
None of them, right.
But would you want to be one?
No.
Also, you have to be thankful that someone is.
So let's get on to large language models. This is an example where you can pick that the large language models aren't working correctly. Well, it's working correctly, it does what it's designed to do, but it's not what people do. So we've got the Wizard of Oz is a good man, what can he do? Now, if I said to you the Wizard of Oz, and I said, you know, he's just over there, you would go, oh, the Wizard of Oz, it's a wizard, Oz is someplace. And then if I said, what can he do? You'd say, I don't know, it's that guy over there, I've got to go and ask him. But if you ask a large language model, it comes up and says, he turned out not to be a real wizard, he was the man behind the curtain, and to the Scarecrow, the Tin Man, the Cowardly Lion. And so, if you're trying to build a large language model to interact with a person naturally, you've got this problem that they're really designed to take the input that you give it, and in that context alone, work out what a response is. It's not designed to iteratively work out, who's this thing I'm talking to? Another example would be if I said Alan Turing, you just get a page of stuff.
Yes.
Yeah, but Alan Turing could also be my neighbour or the person over there. And if you want to have a natural conversation with someone, you've got to be able to introduce topics in the conversation and work it through. So just a couple of points here in context. There's this idea that, there's the idea of short-term discussion. So we're in this room, we can see each other. The things I've said, maybe you'll remember some of them, and you know the things that are in this room. So that's like it's called immediate common ground in the literature, or episodic memory. So this is like an episode. But separately, there's background knowledge. So you know who the Prime Minister is now. It's not in this room, but if I said the Prime Minister, you could say, oh, you mean, I don't know who it is, but oh, you mean this guy? And I could go yes or no, and then we could talk about it and agree. And that way, anything I store after that is accurate. And so I'm building up a knowledge base that I can use forever based on language. So it's a different concept to context than we just saw. Now, I've got a bunch of slides like this. This is just to show off. There's a guy, Robert Van Bellen, put this together. This works for all human languages. He's showing that the main parts of language are, you build a sentence like this. So here's one that says, Hanoko read a book in the library. That's in Japanese, it's Hanoko something, library in, book, read. So the word order is different, but it fits into this where you've got Hanoko, book, read, and it's not shown, but there's this thing about in the library. So all languages follow this, and all languages allow this thing where you can. It's used to be called a noun phrase, so a reference phrase. You can say the company's construction of the bridge in New York City was yesterday or was last year. So you're bundling a whole sentence into one phrase, and then you extend it with one of these. So that's the showing off bit. This shows how the software that I've written handles all of that. So we recognize this sentence, the cat ate the rat continuously slowly on the mat today, evidently because it was hungry. We recognize the syntax of it, and then we map it onto the semantics here, and then we can use it in a conversation. And in the book, I'm talking about this. I've spent 20 years working on the software. I know it really well, but the book is just trying to take a simple view of how all of this works. It doesn't go into this level of detail, but I've got lots of published work that goes into detail.
So programmers for computers look at that universal sequencing of a word of sentences.
Right.
To put things in there, do they?
Yes. So what programmers have done throughout history, if we went back to 1956, they were looking at how do you take words, find the parts of speech that apply, nouns, verbs, adjectives, adverbs, prepositions. How does that fit? And then based on those patterns, they can work out the parse tree, the sequence. They can work out what they think the most likely one is, and then they can map it to semantics. And for the next 60s, 70s, 80s,
so
the next 30 years.
Simple, just very simple.
In theory, people thought it was simple. So for the next 30 years, people tried to create the rules that would make that work. And as Google said when they announced in 2016 their best statistical engine, they said if you take 20 words in an English sentence, it's very possible there's 20,000 possible trees for that, which means no human being's going to write out 20,000 possible trees.
Yeah.
There's got to be something else the brain does because we do it in a few milliseconds. So the solution is that science is wrong. We need to change the science, which is involved in this interaction between syntax and semantics. And then after that, so in 1990, because people had given up on the fact that 30 years of the world's top people trying to solve this problem and not being able to solve it, what people said, well, let's go and do statistics only. And so then statistics were being done with people writing out for each document what the statistic should be, and then the computers took that and started doing what became computational linguistics. Anyway, so and then when that should have died, about 2012, Geoffrey Hinton came out with neural networks with an improved version of statistics, and that's then driven us to the present because it was 10% better than the computational methods, and people thought, well, this is it, we've solved everything. And now with large language models, this is it, we've solved everything. But at some point, we actually have to solve the problems that are unsolved. Yeah. Okay, so this is another theoretical piece. There's a bunch of language-specific things in a language, like what the word order is going to be, and there's a general algorithm for that, which the Roland reference grammar guy has worked out. And then there's this language-independent part, which is how do you get meaning from a sentence. I'll show you that in an example.
Question, John.
Yes?
Maybe it's too early, but is the intonation also part of the semantics?
Is
Intonation.
intonation.
I mean,
It
the man
can't
gave her
be.
the book. It's different to the man gave her a book.
That's called information structure. So that's part of the pragmatics, or that's part of the context.
The discourse.
So it's programmed.
Discourse pragmatics.
Okay, so it's part of context, and therefore,
It's programmed.
in the programming, you have to put
If
an
you're-
addition to it, like there's a stress factor on the verb. Therefore, it's taking out other possible meanings of the same verb.
Right, and it's language dependent. So in English, we can have a sentence with 3 parts. I saw the book, and the default, I think, is the second phrase, I saw the book, and that just tells you that you're adding facts to the context. Right, but if you said I saw the book, you're putting the stress on the first word, I saw the book, as in I didn't see the car.
Yeah.
And so that's all part of the linguistics model. I found this interesting because the world of linguistics always has been very complicated and it works with bigger and bigger numbers. But if you think about it from the theory, so in the theory there's like 24 types of predicates or verbs and adjectives, if you like, which is not a big number. And if we take the meaning see, and then we look at, well, how does English use this word? It's remarkable how flexible that word can be. So the meaning of seeing can be. And so I've got a bunch of examples. So see is here a two-role state. So I saw the computer, it's a state. I saw the computer quickly, doesn't make any sense because it's a state. You'd have to work out what I'm talking about if I'm seeing it quickly because I'm just seeing it. But the same meaning can be applied to an activity which is like watch. So I'm watching the computer. I'm watching the computer intently. You can't see it intently, but you can watch it intently. And whereas this one's the number 11th most popular word in English, watching is the 62nd, or looking at is the 14th. So we've got a bunch of ways to have the same meaning and then package it up with a different word to convey information really quickly. And so as long as we stick to the meaning, we're taking this massive number of possibilities and converting it into something really small. So we're making things work fast with this brain-like model, as opposed to what's happening today with words and word vectors is each word is different depending on the words around it, and you make millions and millions of possible meanings for each word, and then you have to use a computer to work out what's going on. And if I want to cause somebody to see something, could you think of the word? And then I'll take the question. Right. Show. Look. I'll show you this. I'll cause you to see it. Look is the activity which is...
Oh, yeah.
If I say look at it, that's a motion.
Right.
Direction.
Yes, good point. And lots of simple phrases like that have one... So predicates have arguments, so you've got verbs that have things that go with it. If you add something extra to it, it usually makes it causative. So the dog walks, that's got one argument, right? And it means the dog's the one walking. But if you say, I walk the dog, it means you cause the dog to walk. And so that example is again the flexibility that we have in language. So
I was just very interested that verbs have these numbers. Like look is number 14, and what's the other one there? C is number
11.
11.
Yeah.
Oh, so those numbers come from a statistical analysis of the language.
Really?
Yeah. So somebody's gone through and said if you take these billion words, C is the 11th most used, and look is the 14th most used.
So then by using those stats, you get numbers that you can program something.
No, so I'm using that as an illustration.
Oh, okay.
But today's statistical people could use that exactly like that. They convert words into numbers and then they work with
So
the numbers.
that's how the programming happens?
That's how it works today
Wow.
with the large language models.
Where can you find all those numbers? Where is the stats?
Oh, if you do a search on Google for
Statistical... what
for
would be?
100 most popular words in English, and
Okay.
you'll get lots of documents, or 1,000.
Okay.
So it was a really big thing back in like 2000.
Well, I'm sure.
Okay, so when I travel around, a lot of people are really focused on large language models. The reason we went to universities over the last 5 weeks was I can talk to a normal audience, and it's hard to get the distinctions, hard to get the vocabulary right in only a short period of time. But if you're at a university and somebody spent the last 30 years studying something, they're going to hit you with all of the hardest possible questions they can think of. So rather than me trying to refute some argument from an expert in a field that I'm not an expert in, what I've done is I've gone to an expert in the field who spent most of 2024 going around universities explaining what's wrong with large language models. And I like his argument, so I use his. And if you don't like it, well, here's the guy you need to speak to. So this guy, Tom Dietrich, he's a professor from Oregon. He's retired now. And he was saying, what's wrong with large language models and what should we be building instead?
You
So-
have nothing to do with his retirement.
No. He's a really famous guy. He, in the 1970s, was working with machine learning, what we call machine learning today. just continued on. So he's like, you know, the Institute of Electrical Engineers in America, and AIII, the American Advancement for Artificial Intelligence. So he's one of the guys that's a fellow in both of those areas. So extremely well respected, except perhaps by the tech giants that are pushing their current narratives about how this is going to solve everything. Because he's saying that you can't solve it until you do something else. So what he's saying is that the problems with large language models is that there's statistical models of knowledge bases, not knowledge bases. And what he means is that it'll produce something that could make sense, but because it's statistics, it may not make sense. And I don't know if you've heard about hallucinations with today's large language models, but if you don't have a knowledge base and you just generate something that is statistically probable, a lot of the time it's going to be wrong. So that's a big problem. They're expensive. And what he wants to do is fantastic, because it's exactly what I've spent the last 20 years proving we can do, which is separating the linguistic skill from world knowledge. So the world knowledge is what I would call the context, or it's the immediate common ground. And then record and retrieve from episodic memory. So if you're clarifying what you're talking about and then you store it, that's a great repository. You can use that forever. That's a knowledge base. And then you want to create and update world knowledge, because if you do that, then you've got a machine with general knowledge and it's going to work like a person. So at the moment, everybody in this room is just this super AI that we're not approaching at all, because your capabilities are so far ahead of our machines. And then he finishes with there's many details to be worked out. Well, there would be if he was doing it, but fortunately we've done that work. I keep finding scientists like Robert Van Bellen that has these books that explain all these things that you care about with linguistics. And then I find some of his colleagues have done all this deep dive for 20, 30 years into how semantics works. And we're not using it. We, as in technology people, aren't using it because there's a big focus in the tech companies for a certain technology, and everybody's jumping onto that. But we don't have to. We could actually invest money in this alternative space. And so that's one of the purposes of my book.
So are Copilot and ChatGPT examples of large language models?
Exactly, yes. Copilot and large, yeah.
Okay, and so therefore are Microsoft and Google and the like, are they taking input from Thomas Dietrich and these kind of, we should be doing this instead, and are they, to your knowledge, looking to take these recommendations and develop something else?
No.
No.
You said.
No, so all the tech giants are doing the same thing, the same way, and they're all competing to try and beat the benchmarks that they created, that they can pass in order to show that they're improving. And so at the moment there's this incredible improvement in artificial intelligence because they're in control of the tests and the metrics. And so as things keep improving, and it'd be very hard for a single human being to keep up with all of the work. You know, if you published, 300 papers on some very nitty-gritty problems, it's very hard for one person to get across them all and argue about any of them. Whereas for a company with thousands of people working in the same field, they can just keep it going. So it's so my argument is for that. It's good that you have your benchmarks. It's great to see that you're improving. But how do you go against the goals of AI? And then you say, well, we're not achieving the goals of AI. Do you have a robot that can come in here and pick up a book and read a page from it and tell me what it means? Nothing like that. So we're not improving on the goals, but we're improving on the benchmarks. And every country in the world is being told by American companies that this is what you should do because otherwise you'll miss out. But what are you missing out on? You know, something that doesn't quite work yet.
So America is leading in all this digital stuff. Is there any other country that is up there? You said they're all competing to get the best technology or whatever. So rather than content, is America the leading country in that?
Yeah, if you call Google an American company, I would. So Google, Microsoft, OpenAI, they're coming from Silicon Valley.
Okay, so what's a competitor for Silicon Valley?
I don't think there is one. I mean, a company could...
Mona Vale.
Mona Vale, yeah.
You're hearing it right now.
I'm giving you my best pitch.
Yeah, so that's Australia leading the world.
We're leading the world.
You got
Is
it.
it fair to assume that what you're saying is they're shooting in their own foot by continuing on a path with the wrong goal?
Yeah, they've just invested $200 billion in trying to get large
So
language models to work.
Basically a self-fulfilling
But they're
prophecy
not doing
because,
the goals.
because of the investment they continue, but in fact they should step back and reorganize themselves.
Yeah,
That's what you're saying.
What Tom Dietrich would tell us is that there's fundamental limitations that you can't get past. So what you have to do is change the fundamentals of this. And if you went to Google, who might have sunk $50 billion of their money into it, they'd say, oh, I think we'll just try a little bit harder for another couple of years. And individuals or small companies like mine would struggle to compete with a monolith spending $1 billion a year in this area.
So what's the name of your company?
Well, Pat Labs is the Australian company. Pat Labs.
Oh.
Sort of like Bell Labs, but with Pat. And Pat comes from my brain theory called pattern theory. How are we going for time, Beth?
It's 5:30, so you've got 15 minutes
All
before
right.
questions.
What?
It's not finished,
I thought 15 minutes
He's
to-
had questions.
to finish. I've got to get through a couple more things
You've
and
got to
then
get to that video.
we're making questions interactive.
Yeah.
Okay, so OpenAI, Sam Altman is one of the visionaries in the artificial intelligence space, and he's telling people that this year we're going to have solved artificial general intelligence. And what that means, it means that we'll have machines that are as good as people this year. So what that means is that if you're a driverless car and it's raining, so a person can hardly see through the windscreen, so this robot has to be able to see through the rain what's going on. As it comes around a country road and there's a truck parked on the left, there's a 1,000-foot drop off on the left, on the right, on the left, and there's that truck there. And as you come around overtaking the truck, you see something in the road. So this machine, in a quarter of a second, if it's going to be human-like, has to recognize that blob in the road is either a child, some sort of animal, it's a brick, it's a piece of paper. It has to work that out in a quarter of a second, and then it has to make a decision. Okay, well, because it's a child, I'm going to drive off the cliff and kill all the people in the car, because that's probably what I do. Like, a human being's probably going to save the child. Or drive into the back of the truck, and then you probably die anyway.
Or stop.
Well, you can try and stop, but you can't. There's not enough room because you're too fast. So all of those things that's what a human being does now, and that's what you like to think the other drivers on the road are like. Whereas these machines would probably just drive over it, because a quarter of a second's not long enough for it to work out what's going on. And there's all sorts of technologies, there's radars and whatever that they're trying to get to work, but today's robots don't work at brain-like speed.
So is the speed not the ethics of it that you're mentioning? Is the speed not the ethics?
It's the speed that's the limitation. So until the speed is human-like, these robots aren't safe to have on the road, because and it applies to everything. So large language models, if you want to build one, you need about $100 million for the models they built a couple of years ago, and then that 100 million gets you the base model, and then you get people to start manipulating it and testing it and trying to improve it.
Yes.
What about those driverless cars in America?
Yeah, so that's
They're a
exactly.
disaster because they haven't got the speed.
Yeah, they don't have the reaction time. So the technology. Let me get to a key point here.
You're competing against humans who aren't quite logical.
I'm just going to skip through to what the solution is here.
Oh, missing good stuff.
That's okay. We can always come back. Okay. So this is about. This is one of the things we want to get to. Animal skills. So in a brain, what is it?
We're animals.
So here we have a dog. And notice that as I bounce this ball, the dog's turning around 180 degrees. It's hitting the ground. It's watching the ball. The ground's uneven. It's jumped up. It's caught the ball. The legs are off the ground. It's caught it. Now there's a victory lap coming up. So this is just one animal. There's poetry in motion. Now it's got a jacket on. It's more like So this is 180 degrees. So the dog's caught the ball, all legs off the ground. At no stage do you think this animal's going to fall over. She's never fallen over when I've played this game. She's never gotten confused about the fence or the boats or any of that stuff.
This is your dog. Your dog.
It's my friend's dog. My dog doesn't play this game. So this is a $190 million startup in Portland that's got a robot that's got 2 legs. So you can see it can do things like carry these boxes. So I'll just stop it there. So you can see a bunch of blobs here. So this is the sort of vision system that a good robot has today. You can sort of make out that could be some sort of shelving system, and this could be some carts. But for me, when I'm looking at the audience in this room, I can name all the components of it. I can take things that I wouldn't even have a word for, so there's, I don't know, a banner or something. And because I can recognise it, I can then manipulate it in real time.
You know the tapes don't overlap like that.
Oh yeah, right. Yes, going through each other.
Is this what Amazon uses to, put things in and out? Amazon.
Oh, there's robotics, but this is like pushing the limits of technology for bipedal robots. Oops. So here's a Tesla robot that's going to put an egg into that. Notice it just sort of drops it. Right? When you put an egg in an egg cup, you feel it going into the cup, and then you release it. You don't break the egg, but these things, they're being programmed by sight without touch. And I don't recommend you do this at home. So there's our robotics. And so my argument is that we've evolved from simpler animals. And the simplest animals we can think of, like fish, have already solved the problems of artificial intelligence. You've got an early primordial fish or a worm. It's got sensors that connect to its brain, and then it moves with muscles. Right? If it does that well, it eats and it survives. If it's a predator, it eats the other animals and it survives. And if it's prey, it gets away from the predator. So this loop's very important. There's also context here. You saw with the dog when I bounced the ball. The ball's going to be changing shape and size and color, and it has shadows on it. It's got no problem with tracking it. So that's a huge problem for robotics. And it's got a sense of awareness. I'd say that a dog's conscious in the same way that we are. We experience the world, and the difference is we have language and a whole bunch of extensions over here. But if you had an animal brain as part of cybernetics or driverless cars, then you've solved the hard problems of driverless cars. And on this side, you've just got the extensions which humans have, which are predominantly language. But if you think of gymnastics at the Olympics, when people do those complex movements, that's also a high-level brain skill, because we can keep track of these movements. But the underlying brain has solved the main problems. So what's the difference between pattern brain theory and the normal method that they teach you at university about AI? So this method is saying, well, if I take a box and I've just got a whole bunch of templates, and I just put those templates over the thing that I'm seeing, if this one matches, I can say that's a box. And what I was taught at university is this is the model. I take a box, I take its eight coordinates of the points, and then I can use some sort of formula in order to calculate what the box is going to look like. And so if you want to do that in real time and work out that's a table, and I put my coordinates in and then calculate it, it used to take like 3 days to do the computations. And obviously there's something fundamentally different between what we're doing in our brains in real time. It's a quarter of a second to recognize that for a brain, which is...
We did none of that consciously. It's like stepping on and off an elevator when it's stopped. You really notice that it's not moving because your brain's already pre-calculated that you're going to be taken forward when you get on it, and you don't even notice it.
Yes.
But when the thing's actually broken down, your brain still goes, this is an elevator, an escalator, I should move forward. And when you don't, you almost trip.
Right.
And so there's all this cognitive capability that's happening in background you're not conscious of. You're only getting the tip of the iceberg to make decisions on. The rest of it's pre-processed for you elsewhere.
Yeah, exactly. Yeah. So that's the pattern theory model, which is where the brain is keeping track of all the things that happen when we get on an escalator, and because you do that once, well, the next time you do it, it's the same pattern, or roughly the same pattern. And so over time, your brain's got a really good model for what the escalator is going to do, and you know what to do with your feet, and your balance, and sense of touch, and so forth.
And the machine cannot learn to do this? Like once you start giving different kind or more information, can AI learn by itself?
So today's AI, so the large language models, which are the thing that
Yes.
everyone's investing in, they're limited because they learn once, it's the machine learning model, and then they can't learn again until they rerun it. So 100 million, you build your system, you then want to make some basic changes, and you have to relearn the whole thing. Or they can do some intermediate tweaks, but at some stage they have to go and do the machine learning all over again. And that's just the system that's been followed for quite a while.
And so your system is
pattern theory. If I've got a good book here on sale, it's going to
there you go. Okay.
So,
Cass.
so the point you're making there goes back to the point you said that in developing the next model, you need to incorporate sort of episodic learning.
Right.
Right.
Yeah, we want to just emulate what people's brains are already doing, which we know they do because linguists study people across lots and lots of languages, and they find that they do the same thing.
Yeah.
And I've got an example here, which is about this is coming from a large language. I think this illustrates it pretty well, even though you probably can't see it from here.
No, I can see it.
Okay, so this is the large language model piece, and this is Wikipedia. So this is generated by machine, this is curated by humans. And so I asked it about the 1956 Dartmouth conference where AI was named, and it comes out and it says, John McCarthy named it AI, these guys were there, and John McCarthy is the guy from Dartmouth, one of the most famous guys, I think he's behind Lisp. Marvin Minsky is the guy from MIT, Rochester is the IBM guy, Claude Shannon invented information theory for Bell Labs, or for us. And then other notable attendees included Alan Turing.
Oh, really?
So this is not, and that's the point. Like, I was really impressed to know that Alan Turing was at this, because he's my hero.
Oh, yeah.
And so then we did a fact check on it. So this is what the machine's telling us, and it was doing machine learning back in 1956. That's just amazing stuff. But if we then do a comparison, this is the Wikipedia page, and poor Alan died in 1954. And yet this was in 56. So the question is, using your reasoning talent, is it possible that he was there 2 years later? So he wasn't there. And then machine learning was coined in 1959, so 3 years later they called it machine learning. What they were talking about in those days was machines that would learn. So they wanted to build like a child, and then the child would experience the world like a baby would, and then it would learn. So that was the sort of machine learning they meant. But this type of machine learning is, put 100 million examples in, and then get the machine to track that with statistics. And so fair enough, the system doesn't understand that all the things that have happened in recent times don't apply to before it was named. But I mean, knowledge is hard.
So it's fair to say that your opinion is that the current way they work and call AI is not a real intelligent form, because it can't learn unless you really learn the whole system, and therefore it's basically not intelligent.
Correct, yeah. So I don't know if you saw the Super Bowl this year. I was brought up in the US, so I give you my American analogies. So at the Super Bowl this year, there was a whole bunch of ads, and the one that really struck me was the Coca-Cola ad, because they said, we're an AI company. Now, as far as I know, they make Coca-Cola and a whole bunch of soft drinks, but they were really pitching hard that they're an AI company. Sorry, that question?
Yeah, I was just wondering about how Wolfram is different, because they've been working on that for years.
So Stephen Wolfram's the guy behind the Mathematica application, so brilliant guy, and great application for all sorts of reasons. Google, for example, plug into his software in order to do calculations. So he's the, I guess, the computational guru of the IT world. So if you want something computed, he's the guy you go to. He'll get the job done. My argument is that the brain's not a computational engine at all, and there's a fundamental difference between computing and what the brain does. And my analogy would be, in a brain, if you damage the back of your brain, you can't see anymore. Like you don't consciously experience anything. And people with that type of unusual damage, I guess, but people with that sort of damage, if you then show them a book and you say, what do you see? You say, nothing, I can't see anything. You say, well, just have a guess, and they'll say it's a book. So they're still seeing, they're still able to generate in language their experience. And it would be hard to reconcile that sort of damage with the computational model, which says, here's the thing I'm looking for in vision, here's my program that runs it, I'll run my program. You can't not see it and also give the correct answer. So for me, the evolutionary piece, which I do explain in the book, that distinction, which is in a computer you have storage that you reuse.
Yeah.
So when you're learning words or the sounds of words in a brain, you store them in a location. Next time you see that, you experience that sound, you match it, and then you can use it. In a computer, when you hear a sound, you look up through some sort of search algorithm which thing it could possibly be, and you can then statistically say, well, it's probably this memory element. But now you've got to go somehow into the rest of the system with that as your index. So computers work really well for what they're designed for, which is to do ballistics and run banks and all the most of the apps on iPhones. They're really good computational problems to solve. But the things that we've never solved well are the animal type ones, such as I showed with the dog, running around and having sensory experience that it can look.
So who else is on your side with the pattern theory? Like you've got all those people there, McCarthy and whatever.
Yeah.
So you would be in connection with other people in the world, so there must be other people who think like you.
You'd think, yeah, but
they're not.
There's a base of people that follow my work.
Are they?
But so for the last 20 years or so, I've been building the software to demonstrate this. I might just show you what that looks like while we're.
So have you found anyone decent else in the world?
Oh, there's a lot of amazing people. Yeah.
Are there?
So
are you connecting with them?
One of them that we did connect up with face to face for the first time in the last 6 weeks was in Austin, in Texas. And John and he they're both what I'd call cognitive AI scientists as opposed to computer scientists.
Yeah.
So they look at it from a cognitive brain emulation point of view. And John and this fellow's name is Peter Voss, they did a fireside chat, and they're very aligned with the problems of today's AI and what it will take to go to that next generation. Has anyone got what John's done, the pattern theory, brain model, and married with linguistics to implement on a computer? No, John's is unique in that, and as he said, he's got a large following now because people are questioning why we've got these errors, these hallucinations in today's ChatGPTs.
So one of the reasons for writing the book and then for talking to people more generally is just to explain that there's an alternative to today's technology. So I started this last June, wrote the book, which was published around October, November, and now we're just starting the campaign of awareness. If I talk to a typical investor, say in Silicon Valley, what they would probably say is there's this other stuff called AI which is being done by Microsoft, so you can't compete with them, they're too rich. And it's not a good argument because the most popular one was search engines came out in 1980 and they kept ticking over and there was a whole lot of competition for search because it was going to be so valuable. And then a couple of guys from Stanford came up with the PageRank algorithm and they started a company called Google. And within 6 months of them being funded, they were the dominant search engine in the world. And so I think this has the potential of doing the same thing for AI, certainly for linguistics. And I'll just show you this example here. So if I put that into the system, it was the dealer that was sold the car by the man for $1. What the software has done is it's worked out that it was, and then we've got this phrase here which we've validated means something. And when we jump into what that means, just go into this next screen because it's a bit clearer. So this is the phrase, the dealer that was sold the car by the man for $1. And what it's showing us down here is that selling was the main idea. This is that model that I showed you works for all languages. Selling. The one that does the selling is the man. The money that's being exchanged is $1. The man's getting it's the source of that exchange, and the car is the thing that's being swapped, and then the dealer is the recipient. So if we read what it says, the man does something which causes the dealer to have the car and the man to not have the car. So that's the selling part. And then the man has $1 and the dealer doesn't have $1. So there's two exchanges going on in that one phrase. And then once you've broken it into meaning, we can then use it in conversation. So if we just take an
Do we have
example.
developers in the audience? Coders?
All right.
1, 2, 3. Yeah?
This is probably the easiest one to see. So if we have a conversation here, and I say, the shark bit the surfer savagely at the beach yesterday because it was hungry. So as an English speaker, you'd recognize if I said, where did it happen? You'd probably say at the beach. When did it happen? You'd say yesterday. Why? Because it was hungry. So if we then ask one of these questions like, who was hungry?
That's maybe an assumption.
Right, the shark. Because we said here that because it was hungry, and it had to choose from the shark and the surfer
And the beach.
and the beach, right?
Yeah.
So it knows the shark because it was hungry. It wouldn't make sense for the beach to be hungry because it's inanimate. It wouldn't make sense for a surfer to be hungry because if you bite, you die. Right, and so we can then ask, why, and so all of these things are simply taking the meaning of the question, comparing it to the stored context, and then giving the answer. And so what you're seeing is there's language which is language dependent, converted to meaning, and then when we ask a question, we convert it to meaning, compare it to the existing context, and then we pass it to a generator to say what would my answer be in this language, and it then gives us the answer. So potentially this is a technology that's going to allow all of us to communicate regardless of our languages with anybody regardless of their language.
I'd just make a comment. I was checking on a delivery the other day, a very common thing that you do, and all of a sudden this pop up, can I help you? And it was from the AI manager from this delivery company. So it's already, and my granddaughter's in high school and they've been strictly told not to touch AI. They're not allowed to.
Yes, one of
They cheat on their answers.
Yeah.
And also, you're not your kids, but
Yeah,
your
no,
grandkids.
no.
But the other thing is, if you ever pop that up and ask, and say, I wanted to ask about this, they're useless. You haven't got to talk to a human anyway. Yeah.
I don't,
There are some things that have come up where it says, can you tell if this is real or AI? And you go through, and it's very, very hard to tell the difference.
Yes.
So that is simulating human stuff very well.
Yes.
But you think that AI is going to have errors and has a limited capacity.
Yeah, the stats for it are that 37% of the OpenAI, which is ChatGPT, 37% of its answers are hallucinations, so they're not correct.
And what's the technical term for hallucination? Error?
That's my technical term. But believe it or not, the corporates got together and they thought, what's the best way we can deal with the fact that it doesn't work? And they thought, well, if we call it an error, that's not good. But if we call it a hallucination, which is not what it is, a hallucination is where I think I see something, so I give you that answer. These things never see that. What they do is they don't have an answer, so they take the best statistical response.
Has anyone challenged them with that? This
Yeah,
word
yeah.
is around.
So if you look around on the internet, you'd probably find 95%
challenge them.
No, 95% are completely on board. This is amazing. We've solved everything. I can't wait until it takes my job, which it's not going to happen. Versus the 5%. And in fact, here's the best example. If you go to the AAAI, so the American Association for the Advancement of AI, and
Yeah.
they're experts in AI. They did a survey, who thinks LLMs are going to be solving the world's problems anytime soon, or artificial general intelligence. I think they got 75 or 80% that said this isn't on the right path, it's never going to work.
So there are people questioning it.
Yes, it's not just me.
Oh,
That's why I used Tom Dietrich, Professor Dietrich, because
So what are
he's
those
got
80%
credibility.
of people who are questioning it? What are they doing? Just sitting there saying this is not going to work. Surely they've got the knowledge to go around and say, I want to go with this guy, John Ball, because he's
They
got
invite
the...
us to their university to speak.
Yeah, so we've got endless university
And hence we've
schools.
spent 6 weeks doing just that, because we do have an alternative.
Yeah, but who's listening to it? The 80% of people...
We're working on it.
No, but the 80% of people who said it's not going to work.
Here's the challenge with any type of big bubble in economics.
Yeah.
In 2000, there was this big internet bubble,
Yeah.
and if you were Amazon, you were positioned for what they became, but there would have been another, 1,000 companies that said, I'm going to sell
Yes.
books through the internet, and once they went to an investor, they'd say, here's your $10 million, go for it, and they'd then start advertising about how they were going to build a system, and people would get brand recognition and go, well, this is a good company, I'm going to invest. And we're seeing that happen now with this generative AI model. But if you want to argue against it, you're arguing against Microsoft and Google and
Yeah, but
all
you
of
said-
the media.
Yeah, I know, but you said there's 80% of people who
Yes.
know that the current AI is limited.
Yeah.
So what are these 80%?
Well, they're the world experts.
Yeah, but what are they doing apart from saying
Well,
it's
they're probably going to meetings going, yeah, it's never going to work.
But what's a constructive thing they're
Well,
doing? Like you don't just sit there and
investing-
say this is
investing in
limited.
an alternative. Well,
Yeah,
show me the money.
Just
How do you
say-
monetize that? What you create?
Right, so one of the ways is with language learning applications.
Yeah.
So we've got a project underway that I guess we started about 4 months ago with a guy who's a world expert in teaching people language. So he's been teaching Chinese Mandarin speakers how to speak English. And so we're taking that and we're going to convert it into also people who are English speakers to speak Mandarin and basically use this system to get more complicated interactions than technically possible with other technologies. So, and that gets us basically a dictionary for English and Mandarin. When we've proven that, because we have lots of users, then we can take that same source and apply it to different types of problems, like a banking application that needs to interact with the user to get the right bank balance. I did an experiment unintentionally with my banker in the US yesterday. I said, can you transfer money from my super investment into my super fund in Australia? And he came back and he said, I'm not quite sure what you mean. Do you mean the one that we transferred money to, or do you mean within this bank? And so I clarified it with him. And that's what you want machines to do, to recognize that they don't understand and clarify.
That's hard, and that's a hard thing to do.
Yeah,
And
and
that's
today's
so
tech
hard,
doesn't do
can't
it because
Yeah.
Yeah, it was
Yeah.
when the time.
Do you have any medical application for what you've created here to go into industry for the medical people, like deaf people, so forth? So.
yeah. On the medical side, the brain theory applies. So at the moment, if you talk to an expert in neuroscience, most of them will say the brain's a computer. And we don't know how the computations are done for this part of the brain, or that, in fact, for any of the parts of the brain. But if there's some good work that was done in the early 2000s, Jeff Hawkins, that's his book. My argument is that cognitive science needs to use all of the examples that we have to back the theory. My theory takes his work and it improves on it. I came first, by the way. Not that matters.
But we need to continue to learn anything new. We need to learn and not just say, yes,
Right.
it's X, Y, Z. Well, there might be A, B, C, D, E, F, G, H, I,
Right.
all of these other computations.
But the finish. So I think the medical example would be, this is a better model for what the brain's doing, and so we should be able to treat certain types of brain damage more effectively with this technology than with the current model.
Yeah, but I'm still interested in what these 80% of people who
We'll
work
talk
in
to
the
you
industry...
after. I'm interested too.
But, yeah.
We've been kicked out of the
So
room.
sorry to interrupt. No, not at all. Yeah, yeah, you're welcome to ask questions if that's okay while we're selling books. Is that
Yes.
okay? Yeah, sorry, we just have a craft activity for kids in a little while in here. So,
right.
yeah, are we at the Q&A portion of the
Yeah, we-
session? Oh, perfect,
Yes.
awesome. Yeah.
We made it very interactive today.
Yeah, thank you so much for coming, everybody. And you
Thank
can
you.
ask more questions if that's okay with John, like, as we're selling books. Is that will
Yeah,
work? Yeah,
perfect.
great,
Yeah.
awesome.
How much longer then do we have till we get kicked out, Lily?
Sorry.
The craft people.
Oh, like, we just have people setting up for crafternoons for kids at 3:20. So
Okay.
people can sort of have a look at the
No,
books.
we'd love to
and-
talk more. This conversation
Yeah.
is fantastic. And clearly you guys are more passionate and smarter than every university person that we've spoken to in the last 6 weeks. I hope this isn't being recorded. Thank you so much.
I can do edits.
We'd love to keep the conversation going because you've been a great audience. Can I acknowledge, I have a question. I'd like to acknowledge one of the members of the audience who is the wife of the late Ken Trowell, who is one of John's prominent influences into why he's done what he's done. And in John's career in IBM, he was heavily influenced by this great man, Kenneth Trowell, who was responsible for design work of the IBM mainframe. So this is Gene Trowell. There's a lot of great giants in the world, and John stands on the shoulders of many of them. Thank you, Jean, for what your husband, and thank you for your support.
Yeah, Ken would run a workshop on some new topic and would then talk for the entire day, just with all aspects of IBM in this room, and nobody could question him on anything because he just seemed to know everything as it was released. So a real inspiration and an example of somebody that proves how far humanity can go.
And there's a question from this guy.
If hypothetically, if Google came to you tomorrow and said, John, here's 100 million for you to buy the IP for Pat, and we'd like you to lead this program, and we're going to invest in this as another line of business.
Yep.
Would you go for something like that?
Sure. Yeah. Well, I mean, you know,
Look at the
we
terms,
don't need to do it.
terms and conditions.
Anything for a dollar.
Anything for a dollar.
Yeah.
But basically, if they buy my book, chapters 18 to 20 talk about what the world should look like in 5 years' time. So if, I'm looking for across two different businesses, $20 million, and I just say if we had those 20 million, we'd build some languages out, which is the bit that connects to meaning and uses it. And then once we've done that, we have another business that goes, now that we've got this understanding of language, what can we do with it for banking applications and so forth? So there's, over those last 3 chapters, I walk through that. But if you know somebody at Google that wants to talk, we're in
the
that.
checkbook.
Thank you, John.
Yeah, I just want to say thank you so much for coming today, John. And you'll be selling books up the back, is that
Yes.
correct? Perfect. So yeah, that's happening now. Thank you so much for coming, everybody.
Thank you, John. Thank you.
Excuse me,
Thank
John. From just what you said, Google isn't likely to do that to you, is it? Because they're so viewed with that they're correct, or are they wise enough to know that you're doing another branch and they want to get on to the top of it?
They